Okay, so we stopped at example 4.0.5, right, on Tuesday, yeah. So we're going to talk about the probability triple today. Okay, so let's look at the definition of probability measures, right? I think this is just to refresh, okay? So basically you have your set function, right? Your P is actually a set function, and it's defined on a field. It has to be defined on a field, yeah. Okay, not just any particular set. You have to make sure that this set stays in the field, right? Because then only your probability measure will be well defined. Okay, and then of course you have probability 1, 2, and 3, right? So those are things that you are familiar with, at least in terms of just writing down writing down them as facts for you to use, right? But now you have maybe a deeper layer of understanding about such things, right? And at the beginning, we will just define a field, but it turns out that your set function P can actually operate on a sigma field. Okay, but so at the moment we just define it as operating on a field, yeah. But you can extend it to a sigma field. Okay. Okay, so so then with that definition, you can we will be able to derive some results based on those definition, based on that definition, right? So theorem 4.1.1, yeah. You have the following three things which are also familiar to you. One is the monotonicity, right? If your A, B are in your sigma field, and your A is a subset of B, A can be equal to B, yeah. Then the probability measure on A is bounded by the probability measure of B. All right. So intuitively, this is just that the probability measure of the smaller set cannot be larger than the probability measure of the larger set. Okay. Then inclusion exclusion formula for n equals to 2. This one also well known, right? If you have a union of two sets, all right, these two sets need not be disjoint, yeah, and these two sets must be in the sigma, must be in the F, right, in the field. Then PA plus PB is PA union B is equal to the sum of the two individual probabilities. Then subtract the intersection. Okay, I think a lot of you can remember this by the Venn diagram argument, right? But we'll see how to argue it analytically, right? Below in the proof section. And then finally, you have the inclusion exclusion formula, the general form, right? Which is also easy to remember, which goes as follows. If you have A1, A2 until AN as elements in F, then the probability measure on the union of all these sets can be written as follows. Yeah. So you have first the sum of all the probability of all the individual sets. Then you minus the intersection. Yeah. Okay. Your I less than J means the pair is actually, so you're basically just looking at because you just basically look at one particular combination, because A1 and A2 you can swap the position, right? But it just wants one of them. Okay, so that's why you have the sum is less than J. So this would cover like 1, 2, 1, 3, 1, 4, and so on. If you sketch out a table, this is very easy to see. Okay, and then you have then you add. So the next term is you intersect ijk, where your I is less than J less than K. Okay, so basically again you basically just extend the intersection, right? And then keep on doing that until the last one. All right. The last one is you intersect everything. All right, and it's multiplied by a constant, and this constant can be a -1 or 1 depending on what is your n, right? So that's your inclusion exclusion formula. Then from this inclusion exclusion formula, you can show that it you can derive a Boole's inequality, okay? Which is very useful later. Yeah, Boole's inequality is a very useful inequality because it gives a bound to the probability of the union of these sets. All right, in terms of the sum of the individual probabilities. All right. Okay, let's quickly look at the proof. So the first one, although it's intuitive, let's look at how to argue this. Yeah. So your first thing is your B without A, right? And A are disjoint, right? So B set minus A means the set of the part of B that is without A. Okay? And definitely that part and A are definitely disjoint, right? So once you have a disjoint, when you take union, then it's easy to manage. Okay. Yeah. So therefore, the probability of when you take the disjoint, it's just a sum, right? Yeah. Right. So then clearly from here, although I don't know what is P without A, but I definitely know that from here that my PA is actually less than or equals to PB, right? Because my PB actually has PA added with some other things, right? Which is PB without A. So definitely my PB is, so definitely my PA cannot be larger than my PB, right? So you got that inequality. Now the second part, okay, maybe I just write something on the whiteboard. Okay, can you see my whiteboard?
Yes, doctor.
Okay, can you see my whiteboard?
Yes, doctor.
Yes, doctor.
Okay, so let's look at 2, right? 2, so basically you have this. Okay, so basically you have 2 sets, right? So okay. Now first, so you want to find out AUB, right? Okay. Now AUB is basically you should express it in terms of you should express it like this. So AUB is basically this whole thing, right? But you could express it as the following, which is this piece plus this piece, right? Because if you do so, then they are the idea of doing so is because these 2 pieces are disjoint, right? When they are disjoint, when you take the probability measure, you can just sum the individual pieces, right? So basically, you have to first using this idea that you have to sum you express the union of two sets into two disjoint pieces. So the first piece is definitely, so this is one piece, right? And then the other piece is here. Now the other piece is definitely B already. That's B. But what is this piece, right? So this piece is basically your A, right? Your A, you intersect the part that is not B. Okay? So all these parts are your B complement, right? Not inside B. So when it intersects, it basically gives you this part of B that doesn't contain the part of A that doesn't contain B, right? And therefore, when you do this, you have this, right? Okay. Now, so then so we got this part out, but how about this one, right? Okay, so you're looking at this piece, right? So this piece is equal to okay, let's look at it. Okay, so you have this piece, right? So your entire A piece, right? The entire piece of A here is equal to this piece here plus this piece here, right? So therefore, it is A intersect B union A intersect B. Okay, this piece being here and this piece being here. Okay, so therefore your PA is equal to PA and B plus PA and B. Okay, so it's important to express this as disjoint set so that you can when you apply a probability measure, it just becomes a sum. So once you have this, then therefore you know that your PA intersect is equal to PA minus PA and B, right? Then you substitute this inside here, you will get this equation. Okay. All right. So is the idea clear to you how to argue for such things?
Yes, doctor, very clear.
Always try to, when you are considering a set, right, try to see if it can be written as the union of disjoint sets. That immediately allows you to simplify the problem, yeah? Okay, this is actually probably not very challenging. If you look at the more general inclusion exclusion formula, so that is usually shown by using the so you have first you have the individual ones. Sorry, so I just use n first. Okay, this is like one term, right? And you add I less than j, I intersect aj, right? So this start to have two terms, yeah. So basically, if you look at this, it's like your A1, A2 are here until AN. So A1, A2, AN, right? So you are looking at I less than J. So basically, you are looking at things like here, the geometry. So you have to consider the geometry of the table. So basically, it's all concerning up to this point. This point. The diagonal is here. So this is the diagonal. Okay. You only consider this part because this part is redundant, yeah. A1 intersect A2 and A2 intersect A1 are the same thing, right? Okay, so you only need to consider this bit, right? And then you notice that, sorry, this is a minus. It's a minus. Okay, and then you have plus. So it kind of like goes by plus minus plus minus. The sign will alternate, right? The third one is I, J, K. You have I, J, K. Okay, so it's basically like 1, 2, 3, 1, 2, 4, 1, 2, 5, all the way 1, 2, N, and then you repeat 2, 3, 4, 2, 3, 5, and so on, right? Okay, and then you keep adding until the last one. So the last one, the last one will basically have intersection of everything. Okay, and whether it is positive or negative will depend on here, right? If your n is odd, this will be positive. If it is even, it will be negative. All right. Okay. So to prove this, we use induction. Okay. So induction, we do induction. Then the idea is the following. All right. So first you check n equals to 2, right? N equals to 2 is definitely correct because of we already proved it just now, right? For the specific case, right? Then you assume to be true. You assume to be true for n equals to k, right? You assume this equation to be true for n equals to k, and you want to show that for n equals to k plus 1, okay, I use a different notation, right? Sorry, I use k equals to n, right? It doesn't matter, right? I use my indexing, I use k, okay. So it's okay. This is k equals to, sorry, n equals to 2. Right. Okay, so so we assume the equation here to be true, and then we want to show that when k equals to n plus 1, this will basically just switch to n plus 1, right? So basically this will end up with n plus 1, this will be n plus 1, n plus 1 plus 1, okay? All right, so how do we do this? All right, okay. So you assume k equals n is true, okay? Then when you have k equals to n plus 1, right? So basically we are interested in this thing, right? And this is basically equal to 2 parts, right? So you have to make use of the previous results. So one part here, union a n plus 1, right? So basically you can treat this as your A and you treat this as your B. And you apply the result that is well known for at this level. So this will be union AK plus P of AN plus 1 minus P of union AK intersect AN plus 1. Okay. Right. So over here, you apply your inclusion exclusion formula, right? So you apply the inclusion exclusion formula for this part, you will get that long thing there, and then you got this one, right? And then again for this part, right? What happens is that you will get. So you have to see what this actually means. So what is this? So basically you have A1 union A2 union until N. Then you intersect AN plus 1, right? So basically this is equal to A1 intersect AN plus 1. then union A2 intersect AN plus 1 and so on, right? Okay. All right. So basically, so you can basically just put a bracket here. Okay. And therefore you treat this whole thing as one thing A, right? And then you apply your inclusion exclusion formula on this object, right? And after that, it's just rearranging, right? Rearranging the results. Okay, you will get the inclusion exclusion. You get the inclusion exclusion form by just replacing your n with n plus 1. Okay, so so this is just to give you the idea, right? Okay. For actual, I'm not going to ask you to prove these things, right? I'm just outlining the way you can argue for such things, right? Because that's not the purpose here. The purpose just to because this is just a small part of the result. So, but just to let you know, okay? All right. And then for part 4, you want to prove Boole's inequality. Which is okay, it's bounded by this. Okay. Okay, so let's see how the proof actually goes around showing it, right? So you let B1 equals to A1, right? Then you have B2 equals to AK, sorry, the BK equals to AK intersect A1 and so on. Okay, so therefore your BK are disjoint. See, the idea is you create disjoint things, right? You see that your BK, right, is the part of AK that does not contain the others, yeah? So basically this means that the part of AK that does not contain other AIs, right? Because you have AK, you intersect with the part that is complement to A1, A2 and all that. So definitely it will be the part of AK that does not contain A1 and all that. So if you think of your sets like this, they're all tangled together. Like for example, just A1, A2, A3, right? So it would be like, so your B1, so your A1 will be, your B1 will be A1. The whole thing, this will be your B1. And then your B2 will be, in this case, you submit B2 will be A2 intersect A1 complement, right? So the part of A2 that does not contain A1, so that would be here, right? Okay. And then finally, your B3 will be A3 that does not contain A1 and does not contain A2. So it will be this part here. Okay. So and so on and so forth, right? So basically, it's just all disjoint, yeah. So once they are disjoint, then when you consider P union AK. So this is union of everything, right? So it's the whole thing, right? But the whole thing is basically equal to you union the disjoint parts, right? It's the same, isn't it? So you take the union, the whole thing is like you add up all these fragments, right? You're basically adding up these fragments. You add up this fragment, You add up these fragments, and you add up these fragments, okay? So you add up all the fragments, right? So this is correct. And now you'll see that because these are disjoint, you can write it as P of sum of P BK, right? All right. Now, but your BK, right? Your BK is actually a subset of AK, isn't it? Right? Your BK is actually just a small part, isn't it? Right? You look at this, it is actually a subset of your AK. Therefore, you by monotonicity, right? Property 1, you will get summation P of AK. Okay? So the argument is actually very nice, yeah. In fact, this whole argument is very lovely because of the way it actually considers the how it constructs the disjoint sets and then take their union and then apply the monotonicity property. All right. So it's a proof that it's worth the ideas there are worth learning. All right. Okay. So is it clear to you? For this example.
Yes, doctor.
Okay, so great. So now I want to, so we have already talked about construction of the probability triple, yeah, right? How you have to construct your sigma field properly in the property triple so that you can meaningfully talk about some the property of the sets that you want to talk about, right? And let me see, let me switch the screen. Okay. So this is the example that I discussed, example 4.1.3 on Tuesday. So basically for this question, right, if you want to answer this question, of course, you just need to construct your F in such a way that it allows you to answer this question, right? So in this case, since your omega is actually it's actually in an infinitely large set because you want to consider all possible directions, right? So that would be from 0 to 2 pi, yeah? Circular, right? For this example, that will be, well, we can construct a space like that, but that will be a kind of like a Borel space, okay? But let's say we make it simple here. Just construct your F to be the following, right? This is definitely a sigma field, okay? Empty set, the omega, and then you have east and not east, right? You just lump everything together. So the east, the complement of east is not east, okay? So finished. This is a sigma field. Then you can create your probability triple, omega, F, and P. And therefore, since your east, right, is an element in F, therefore it's meaningful to talk about probability of east. Okay, and then you can assign any value to it. Doesn't matter, from 0 to 1, any value you like. As far as the construction is concerned, there's nothing wrong with the construction. Okay, so it's just that any value that you assign to it, right, is a reflection of your belief. Okay, that your degree of belief that the sun is going to rise from the east tomorrow. Some students said 1, right? Well, that is a reflection of belief that you are certain that for that person, yeah, he's certain that the sun is going to rise from the east tomorrow. Like if you play a game with him, you ask this question, he's for sure that he's going to guess that it's going to be east, and he's very confident about it, right? Okay. Okay, so the next thing is now if you have if you want to ask about the probability that the sun will rise from the west, okay, then your construction is actually incomplete. Yeah, your F does not include west as one of its elements, right? Because northeast doesn't mean it's west. Yeah, northeast simply can mean north, south, and whatever, right? Southeast, whatever. Okay. So therefore, you cannot discuss probability that the sun will rise from the west tomorrow. It's just undefined. That probability cannot be discussed. Okay, because you are trying to map. You try to take an element that is not inside the F and map it to 0, 1, and that's not allowed. Okay. All right, so I hope that you have some idea. Yeah, the main idea here is that in order to discuss probability properly, you have to define your F. You have to construct your F properly. Yeah. Okay. All right. Okay. So now that I think I'm done with this example. So I've got some new material on something called the Lebesgue measure. So this part is actually also quite simple. Let me go to my Lebesgue measure. So this is the last thing that we're going to talk about for this week. Lebesgue measure on the unit interval, right? Okay. So basically the Lebesgue measure is so when you have certain sets, right, you want to apply a certain measure to it. Okay, so the measure that we are discussing here is something called the Lebesgue measure. Right, this is read as Lebesgue. Okay, in case you find that this is very hard to read, right? These French names are hard to read, right? So it's read as Lebesgue. Okay. Now, suppose you have the following. Yeah, so you have 0, 1. Okay, so you construct. So maybe I construct like this first. Okay, you construct any subintervals, right? That means you take any subinterval like this, right? It can be anything. Okay. So you got many subintervals, right? Possibly. Okay, and then you can collect them together in some collection I, which is basically a Borel sigma field. Okay, you can collect that, right? And then you define the so for any element here, right? So for any element in the Borel sigma field, you can let's say this is defined as this. Okay, so you define lambda, the Lebesgue measure, lambda, the measure on this I, yeah, as equal to the length, yeah, the length of this interval. Okay. So basically, what happens is that you have this field here, right? So there are many. So this I here contains many sets, right? It can contain all sorts of sets, all sorts of intervals, all sorts of subintervals. Okay. Of 0, 1. So basically, your lambda, right, takes an element here. It takes an element here, and it maps it to SIT3001. Depending on so the way it maps it is that if here, right, the is an interval a b, so it will map it to the length b minus a, so it will be here. This will be your b minus a. Okay, you will put it there, right? It puts it there depending on the length, okay, of the interval. So it's very simple. All right, and if you have these are if all your I are disjoint, yeah, right, and your A is union of their union of all these disjoint intervals, then the lambda of A is basically you just add up the individual lengths. Okay, so that will be just bi minus ai. Just add up all the lengths. Okay, it's very simple. Okay, so because of this, we say that lambda, right, is a set function on the Borel field. Again, it's a set function on the Borel field B naught, which can be extended to the sigma field, the Borel sigma field. Okay. All right. So the usual introduction is that you first talk about lambda as a set function on a field. Then it turns out that it is also a set function on the sigma field, right? Remember that the sigma field contains countable intersection operations, yeah, whereas your field does not contain countable intersection operations. Okay. Now, so once you extend it to the Borel sigma field, right? You have the following property. Okay. First thing, right? If you haven't extended, okay, if unextended, so lambda of I, clear this. Suppose your I is a Borel field, okay, then lambda of this is undefined, where your x is a singleton. Okay, singleton, it means singleton in the unit interval. So it's undefined. That means if you want to put a Lebesgue measure on one particular value, right? Maybe 0.1, 0.2, it's undefined. Because your singleton, right, does not belong in a Borel field, okay? It turns out that, but if your I is a Borel sigma field, then the Lebesgue measure on the singleton is defined and equal to 1. Equal to 0. This is very interesting. So the way you argue this is as follows. All right. So the way you argue it is as follows. So you know that the singleton, right, is actually the first we think of it like this. First we consider something like this. We take the intersection of these intervals. Now I'll take my n from 1 until some fixed number, let's say k. Or actually, I might actually just use k as the index here and put n there. Doesn't matter. This may be more familiar. Okay, so think of this intersection, right? So basically is this thing. So you have 0 to 1. So this is your particular x value. Okay. So first you have x minus this, right? So it may be some. So it will go out of here. So it will be something here. Doesn't matter, right? And then you have 2, right? So when you have 1 minus 2, so it subtracts less, so it may come in here, right? And come in here, right? So this will be the case for k equals to 1, k equals to 2, k equals to 3, and so on, right? Until the case of k equals to n, right? Okay? So you have all these intervals. If you take the intersection, right, it is very clear that the result is the smallest interval here. So definitely this is equal to x minus 1 over n x, right? Because all these other intervals are larger than it. We'll take interval, definitely is this interval, right? The shortest one. Therefore, because, right, your limit of n tends to infinity, you take the intersection. Is equal to the singleton, right? Because as you keep taking this, right? If you keep pushing this smaller and pushing the interval to be smaller and smaller, eventually it will just hit your value x here, right? So your singleton is actually equal to the limit of this intersection. Or sometimes we will just write it as, we just replace it like this, right? So this means this is a countable intersection. Countable intersection of sets in the Borel sigma field. Okay. So therefore, when you try to measure this thing, right? So we'll try to apply a measure on this thing. So you put a measure on this thing here, right? You put a measure on the intersection is the same as you put a measure on this interval, right? And the measure of this interval is basically just the length of this interval, which gives you 1 over n. All right. So the measure of this intersection, right? This finite intersection is basically just the length here, which is 1 over n. And since the singleton is obtained after you take countable intersections, therefore it's very clear that your measure of the singleton, right, is the limit of 1 over n going to infinity for n, right? And therefore this will tend to 0. Okay, and this shows you that the lambda of the Lebesgue measure on a singleton is equal to 0. Okay, so you might have been puzzled like last time when you studied probability, right? Let's say you study a continuous distribution, right? Like the normal distribution. So you might be puzzled that you can find the probability of some interval, right? When your random variable has some continuous distribution. But people never discuss things like the probability of getting a particular point, okay? Now you can understand that actually the probability measure for the singletons will be actually 0, okay? Once you understand the Lebesgue measure.
Excuse me, doctor. Can you let Om inside? She can't enter.
Sorry?
Can you let Om inside? She can't enter. She's waiting in the lobby.
Already.
Okay, thank you.
Yeah. Yeah, so just to be clear, like last time you studied things like this, right? So this is your normal density, still a standard normal density, right? Jiasheng, what is the equation for the normal density?
Uh, 1 over square root 2 pi sigma square.
Standard normal.
Sorry? Oh, standard normal is 1 over square root 2 pi times exponent to the power of 1 over 2 x squared.
Okay, good. You must know your normal density like the back of your finger if you are a statistics student. Okay, this is like asking a biology student what is the nucleus of a cell. Okay, must know this. Actually, it's actually easy to remember because you know that there is a constant here. The constant will involve the square root 2 and pi. And over here, it's basically an exponential function, but with the x being squared, right? And that's a factor of 1 over 2. Okay, must remember this. Okay, so of course, you may have studied things like let's say something like this, right? Now later, so for example, you studied something like this, right? Okay, and then this is calculated as the area under this curve. Now later, as we go along the course, you will start to understand how these things are measured. Later you will start to know something called the Lebesgue integral, right? That's how it's actually being calculated. And then later you will also study why this kind of statement, right? In fact, is actually equal to 0. Okay? Remember in your elementary probability classes, you only calculated probability of intervals, right? Never really talk about points, yeah? The probability of points. In fact, if you have a countable set, even if you have an infinitely large set, just maybe some values, just in, let's say the set of integers, right? Positive and negative integers. This is an infinitely large set, isn't it? But the probability is still 0 because this set is countable. And it turns out that the Lebesgue measure of a countable set is actually 0, right? Just like the previous example that you saw, the Lebesgue measure for a singleton is 0. So your countable set, right, is actually the union of many singletons, right? And they are all disjoint, okay? So because of that, you basically just have the sum of the individual Lebesgue measures of 0. Okay. So now finally you can have some understanding about such things. So we'll learn more about this when we go to the when you come back for the subsequent things. We have something called Lebesgue integral. Okay. All right. Okay. So just to complete the material here, so we have now several facts here. So the Lebesgue measure of an interval is equal to the length. The Lebesgue measure of a singleton is equal to 0. The Lebesgue measure of a countable set is still 0. This actually comes from 2, yeah. Okay. And finally, so you might think that okay, so singletons fine, countable sets, yeah, Lebesgue measure is 0. You might think that 0 just applies, the Lebesgue measure of 0 just applies to this kind of condition. Not actually. There are number 4 here. There are uncountable sets. This is still countable, right? These two are countable. This one is finite, the other is countable. Okay. there are uncountable sets with lambda. Uncountable sets, let's say A with lambda A equals to 0. Okay, so the example that we're going to talk about is the Cantor set. Okay, which is a very well-known example here. So let's look at the example of the Cantor set. So, okay, you build the Cantor set like this. So the Cantor set is built like this. So this is your, okay, this is 0, 0, 0, this is 1, yeah? Now, so you first divide, the algorithm works is as follows. So you divide it into 3 parts. Divide into 3 parts, and then you dig out the middle, remove the middle 1/3. So this one remove. But you remove not including the points, yeah? Remove the empty, remove the open set, right? So you dig out. Okay? Remove that, right? Then, so step 1, right? So you okay. So you step 1, you remove this part, right? Step 1. So then you are left with 0 to 1/3 and 2/3 to 1, right? Okay. Then you repeat the operation of cutting into 3 parts for the remaining intervals. So you will cut into 3 parts. So one part is here, right? Something like this. Okay, 3 parts, right? So definitely this will be 1, 9, 2, 9, right? So this part the same, you cut like this. This will be 7, 9, 8, 9. Okay. And then again, you remove the middle 1/3. The idea is you repeat this, but you keep on doing the same thing, right? Remove the middle 1/3, right? Of the remaining, but not including the endpoints. Okay. So your Cantor set, right? Just now will include 1/3, 2/3. Because the singletons are there, right? You are removing the open interval. So now it will include 1, 9, 2, 9, and 7, 9, 8, 9. All right. Okay. Right. So for step 2, yeah. So you remove this. And let's do one more step. So step 3, you remain with this interval. Now you get 4 intervals, right? So you will remove, you cut the remaining intervals into 3 parts again, right? And again, remove the middle 1/3, right? So remove this middle 1/3. So left with the endpoints. Okay. So now over here you will have, so this is 1/9, right? So 1/9 divide by 3, there will be 1/27. This will be 2/27. Okay. So then for this value, this will be times 3. So this will be 7/27, 8/27. Okay. And so on, yeah. So you can work out the points there. Okay. All right. So again, you can add the points there. So that will be 1/27, 2/27, and so on. Okay. Right. And then you keep on doing this without end. Just keep doing. right? So the Cantor set is equal to whatever is left at the end. So therefore, your Cantor set is keep increasing like this. So it will definitely include these singletons, but towards the end, you will never actually get you will never actually get all singletons, but rather towards the end, right, you are going to get some the set here will include some intervals that are extremely small, okay, but they are not singletons. All right. So your Cantor set is actually uncountable, yeah. Okay, because it will contain some intervals that are very, very small, right? In addition to the this countable set here, right? So it's basically the union of a countable set consisting of all these points, and so it will be this countable set union some very small intervals. Okay, so these very small intervals are very abstract. All right, so they are so we just discuss them as a concept here. Okay, so now how do we measure? So let's say you define Cantor set C. So how do we measure C? So it turns out that we use the idea of complementation, right? So we will first measure the complement of the Cantor set, right? Which is the part that is being thrown away. So this turns out, because these intervals can be measured, like this first interval that's thrown out is 1/3, right? The length is 1/3. Okay. Then the second step, right? You throw out this interval and this interval. So that will be, so the first interval is 1/3 plus, okay. The second interval will be 1/9, right? So this is 1/9. Okay, it's 1/9, but you got two pieces. Okay, first piece is 1/3. The second piece is 1/3 of the previous one, but there are two pieces, right? Then and so on and so forth, right? Then the third part is you got three pieces here. Sorry, you got one piece here, right? So then that will be, you duplicate that, so that will be 4, right? And so on. Okay, so you basically the Lebesgue measure of the complement of the Cantor set will be equal to this sum. All right, because they are all disjoint, yeah, so you can sum them together as sum their lengths. So basically this one, if you look at it carefully, this is equal, the general form is 2 to the power of n minus 1 over 3 power of n, right? Where your n is starting from 1, 2, and so on. Okay, so basically you sum this. So this is equal to the sum. So this is actually a geometric sum, right? You can write it like this. Okay, the n minus 1, you group the common exponent n, take out the factor of 1/2, yeah? Okay, so this will give you what? So this is easy to do if you remember your geometric sum. So this is it. Take out a common factor 1/2. So this will be 1/1 minus the common factor 2/3, and that gives you no, not that. So you have to factorize a bit first. Maybe I clear this. So you have the Lebesgue measure on the complement of the Cantor set is equal to 1/3 plus 2/9 plus 4/27 plus so on, right? Which is equal to sum of 2/3 n power So you have this, okay? Which allows you to write this as 1/2 sum of 2. Okay. But this one is not starting from 1, yeah? Your geometric sum starts from 1 plus r squared and so on, right? So equals to 1/1 minus r if your r is between 0 and 1. So here you will, in order to start from 0, so you subtract 1, right? Okay? From 1 go to 0, you subtract 1 on the index, but you have to compensate back on the summand, okay? So that you see that when your n is 0, you put 0 here, you start at 1, right? So the usual operation here, if you subtract 1 on the index, you will add 1 on the summand, okay? So then this will be, then this is a common term, right? Sorry, this is a constant, so you can take out 2/3. So basically you have the sum here. So this is your geometric sum, yeah? Geometric series, sum of geometric series. So basically this is equal to, so you cancel this 1/3 times 1/1 minus 2/3, okay? And therefore that gives you 1/3 times 3 equals to 1. Okay? So the Lebesgue measure of the complement of the Cantor set is 1. Therefore, I know that the Lebesgue measure of the Cantor set union its complement is 1, right? Because this in union is the 0, 1, the 0, 1 interval, right? But then so your Lebesgue measure of C plus Lebesgue measure of its complement is equal to 1. But this one is 1. So therefore your Lebesgue measure of the Cantor set is 0. Okay? Despite the fact that your Cantor set has many things inside. In fact, it is uncountable. But its Lebesgue measure is actually 0. Okay, so this gives you an example of an uncountable set with a 0 Lebesgue measure, right? So 0 Lebesgue measure does not mean that there's nothing inside the set. Okay? Of course, definitely Lebesgue measure of an empty set is definitely 0, right? But there are many more other sets that can have Lebesgue measure of 0, okay, without being actually empty. Right. So that's the idea of your Lebesgue measure. Okay. So are there any questions about this part here? About the Lebesgue measure? Any questions? Okay, so you might want to watch the recording later if you feel that the explanation is you're not able to fully integrate the material yet. Yeah. Okay, don't worry. It's not very difficult, right? This thing is actually not very difficult. It just looks difficult. It's actually not. Okay. Right. So let's take well, let's take 5 minutes for stretching, and then let's take 10 minutes for stretching, right? And then we'll come back for the remaining 2 questions in several questions in tutorial 2, right? Then I just say something about tutorial 3, and then we can stop, right? Okay. So you want to share your screen, Pavan?
Yeah, yes, doctor. Doctor, I think you need to stop sharing. Stop sharing first.
Oh, okay. I stop
Yeah.
sharing. Okay.
Okay, doctor, can you see my screen?
Yes.
Okay, so for question 4a, we have to find the limit infimum and limit supremum for the sequences. So this is our sequence here, xn equals to 1 plus negative 1n. So when we expand the sequence, this is what we get,
Okay.
0, 2, 0, 2. So for supremum xn, we get 2. And then the limit supremum xn is going to be 2 also. And
Yeah.
then infimum xn, it's 0. And so the limit of infimum xn is also 0 for all n which is in natural number. So next the question asks us whether the sequence converges pointwise. So the sequence here oscillate by values of 0 and 2. So xn does not have limits, so xn does not converges pointwise.
Yeah. Okay.
Okay, next I continue to the next sequence. So this one is xn equals to cos n pi over 2 plus sine square n pi over 2. So when I expand the sequence here, so these are the values I get. So as we can
Actually, it
see,
keeps on going. Yeah.
yeah, it keeps on going, but we can see there is a pattern here where the sequence repeated every 4 terms.
Yeah. So, yeah. Right. But you when you write you have to write dot 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 before you close.
Oh, okay, here, doc.
Otherwise, it means finite sequence.
All right, okay, sir. Okay, doctor. So for supremum, we take the repeated 4 terms, and then from there we got our supremum, which is 1. So our limit supremum is also
But actually, Pavan,
yes, doctor.
you cannot take the supremum of that sequence by taking a supremum of a subsequence. Although you have to consider the whole thing, right?
Okay.
Your argument is just that in that whole thing, it never runs above 1 and it never goes below -1. That's all. So your argument is slightly a bit it's not
Incomplete.
watertight lah.
Okay, so it's going to be overall sequence.
Yeah, overall, so you can't put the supremum of a subsequence there.
Okay.
Although the answer is correct, but the argument is not watertight.
Okay,
Because
so
you
I
look at the whole thing. Your basic argument is just that sequence will not get out of it won't get out of 1.
-1, yeah.
Okay, it won't get out of 1 and it won't get out of minus 1.
Yeah.
Yeah. So that's all. You can just say your sup of xn is equal to 1 and your infimum is equal to -1 and yeah.
Okay, so I think I'll just add a dot dot here as it continues. So it's 1 for supremum and infimum is going to be -1. So here the sequence oscillates by 1 or -1 also.
Okay.
So limit does not exist and xn does not converge pointwise.
Okay.
Thank
All right.
you, doctor.
Thank you, Pavan. Okay, I think that's quite clear. Yeah. The finding of the lim sup and lim im for those two particular sequences. Okay. The next thing, Albert, you want to share screen?
Yep, hold on. Okay, can you see my solution?
Yes.
Okay, so this is for 4C. The xn is 3 to the power of -n. So we expand it and we get the tail sequence. This is the tail sequence. And from this value, we can find that it is a decreasing sequence. So since it is a decreasing sequence, the supremum of the tail sequence will be the 3 power to -n. So we get the limit to n over infinity and we get the 0.
Okay.
Well, since this is a decreasing sequence, we know that this value will keep on decreasing until 0. So the infimum will be 0. And since these two limit is converged to 0, the xn is actually converged to 0 and the xn is pointwise converged to 0.
Okay. Yeah.
All right. So for the 4D, when I expand it, I found out that there's a negative and positive. So I try to sketch it out. Well, this is the tail sequence. So from this graph, right, we can find out that it actually converges around to 0.5. So since that it is from here, we can see, oh, it is a decreasing sequence. So we know that the supremum is equal to this term, and we found the limit to the n to the infinity, when we found the limit is 1 over 2. And from the infimum, it will be 1 over 2. So since these two terms are converged to 0, so the xn will be converged to 0 and the pointwise converged to 1 over 2.
Converge to 1 over 2.
Yeah.
Not 0, yeah?
Oh, sorry, it's converged to 1 over 2.
Yeah, right. So yeah, okay. Yeah, the argument is okay. All right, okay.
Okay.
Thank you, Albert.
Just stop
Yeah,
sharing.
please continue.
All right.
Okay, thank you. Okay. I think it's a quite simple exercise. So if you have if there's pointwise convergence, you will find that your lim sup is equal to your lim inf. If your lim sup is not equal to lim inf in your sequence, then there's no convergence, right? It's either divergent or it can be oscillating, right? In those two cases, we saw oscillations. Yeah. Okay. So let's go on to problem 5, Karim.
Yeah, okay, doctor.
Just share your screen. Okay.
Okay, is my screen share now?
Okay.
Okay, problem says that show that fnx equal to 1 over nx converges to pairwise to 0, but not uniformly on 0 to 1 as n goes to infinity. And then he give us like the hint is n1, 2, 3, 4. Then I have to draw the f of these n values. Okay, here. Okay, here the solution is this one are the f1 of x. I draw here f2 of x, f3, then f4 of x. Or f of x, fn of x is 1 over nx, which is f1 of x is 1 over x, and the x is the value of x is from 0 to 1. Should be all a positive sign, a positive line here, this side. Okay, n limit of n goes to infinity, fn of x equal to 1 over nx, it goes to 0. It is pointwise to 0, because here if let's say if you take like f200 goes to 0, is this one in this area, because it goes down to here or like epsilon. Here these are two horizontal line, one and two here. It goes to here. However, it does not uniform convergence. Yeah. Is it clear, doctor?
Well, okay. So the argument is that your epsilon, if you push your epsilon somewhat a bit higher, then it may be clearer. Because if your epsilon, right, just push a bit higher, you will find that it will intersect the functions at the early parts, right?
Yeah, like around here, right?
Yeah, well, you push it a bit higher, so it will intersect, right? That means for those values of x that are close to 0, right, you'll find that the function value, they escape epsilon already, isn't it?
Yeah.
That's the whole point, yeah, because they cannot escape epsilon for whatever function of for whatever values of x when you tend to infinity. So yeah, if you push the epsilon line a bit higher, that may be easier to
Okay.
see. Okay. Thanks, Karen.
Thank you. Can I stop sharing now, doctor?
Yeah, just stop sharing. So maybe what I wanted to say just now was you could have you could do something like this. So your curve was like this, right? So 1 over nx. So this will be like this. 1 over x. Then you have 1 over 2x and so on, right?
Yeah.
Okay. Right. So basically, if you put an epsilon, let's say you put epsilon here. Okay. First, so this is 0, right? You want to check whether it converges uniformly to 0 or not, right? So 0 is flat line, right? So this is your epsilon, right? So that would be your fnx minus 0 bounded by epsilon, right? But you see very clearly that no matter what you do, only certain sections, like for example for this curve, it's only bounded starting for values of x more than that. For this range, right, it's not bounded, right?
Yeah.
It's already gone out of the epsilon. Same for this function, right? So it's gone out. In fact, no matter what you do, even you set your n to be very high, it will be, because your this function, right, it immediately will shoot up. You see, for very small x, it immediately will shoot up. Okay.
Okay.
So no matter what you do, there will be some. You can always find there will be always some n, right, such that this fn of x minus 0 will exceed.
Okay.
Okay, no matter what you do, because it just increased too quickly. It doesn't matter, because your uniform convergence, you must ensure it for all x in some defined interval, right?
Interval.
Okay.
Okay.
Now, having said this, it is 1 over nx is not uniformly convergent over x in 0, 1, right?
0 to 1.
0, 1. How about in 1 over 2, 1? Is it uniformly convergent in 1 over 2, 1? Your 1 over 2 is, okay, so in this example, I already cut at 1, right? Okay. So 1 over 2 is here. Is it uniformly convergent in 1 over 2, 1? Karim?
Yes, doctor.
Yes.
Yeah.
In fact, yes, because for 1 over 2, right, you see that you see, for 1 over 2, if you keep increasing the n, they will just go lower and lower like this.
Yes.
Therefore, you can always you can always find some n such that they are bounded by some arbitrary epsilon. But it is not uniformly convergent over 0, 1, because for when it's close to 0, right, it shoots up too quickly. Okay?
Okay. Yeah.
But uniformly convergent over 1 over 2, right? So whether a function is uniformly convergent or not, it's not a universal property. It depends on what interval of x you're talking about. Yeah? Okay, it's with respect to the interval that we're talking about, right?
Okay.
Okay. So I think this is a good example to illustrate that point as well.
Doctor, how if in case if they gave us like the x goes to minus 1 to 1?
Minus 1 to 1, so you have to, let me,
Yeah, draw the other side. Negative.
so you have to draw the other side.
Yeah.
That will be, so it will be something like this, and then minus 1 to 1, right? So if the other side, okay, so that will be something like this. Let me see how this would go, like this. Okay.
Okay.
Yeah. So, well, clearly this is not, it won't be uniformly convergent because you can always find some. So in this case, you go like this.
Yeah.
So you cut like this, right? So there will be always some parts here, right? The parts here up too quickly. Okay.
Yeah. Okay.
Okay. So
Thank you.
yeah. Okay. Okay, that's a nice discussion. So can we move on to problem 6? The Zafira. Zafira here. Yeah.
Can you hear me, Doctor?
Yeah, but a bit on the low side, the volume. Maybe you can increase the volume a bit. Okay, just share your screen.
So for problem 6, the question is let f and x equals to sine n x over n squared plus 1. Show that f and x is integrable over the interval 0, 1. This can be done by showing that integration of 0, 1 f and x dx is less than infinity. After this, show that f and x is uniformly convergent over the same interval and then proceed to find the limit. So f and x is equals to sine n x over n squared plus 1. And for the integration, we will get equals to 1 over n squared plus 1 less than infinity. So the conclusion is f and x is integrable over 0, 1.
Okay.
Okay. And for limit n approaching infinity, f and x equals to 0. So sine n x over n squared plus 1 minus 0 is less than equals to 1 over n squared plus 1. And less than equals to 1 over n squared. And less than equals to 1 over x squared less than epsilon. And we choose n greater than 1 over square root of epsilon. Hence, f and x is uniformly convergent over 0, 1.
Okay.
This justifies the interchange of limit and the integration. And for limit n approaching infinity, integration of 0 to 1 sin x over n squared plus 1 will get equals to 0. Okay.
Okay. Yeah, just a slight comment here. Yeah, it is okay. The general argument is correct. Just maybe slightly minor. Can you push up a bit your slide? Okay. So over this argument here, the absolute of, so you're trying to find the deviation of f and x from the limit, right? So it's bounded by 1 over n squared plus 1, and it is bounded by 1 over n squared. Okay. In this case, I think it's a strict equality.
Strict.
Yeah, because your 1 over n squared plus 1 is definitely strictly unequal.
Okay.
It's okay. These things is a minor thing. Sometimes we will just write it like that.
Okay.
But yeah, you may just change it to just a strict inequality.
Okay.
Yeah, and then yeah, you're right. It's bounded. In fact, directly. Zafira, the simplest one would be it is definitely bounded by 1 over small n. Then your n is actually much simpler.
Okay.
That will do also, but of course, there are, as I said, there are many ways to do it, right? So
Yeah.
this is also okay, yeah.
Okay.
Okay. All right. Thank you.
Okay. Thank you, Doctor.
Okay. So that's a clear explanation, right? So the whole point of this exercise is that if you want to find the limit of some integral, where that integrand actually involves n, then you should check for one way is to check for uniform convergence, right? You show that the uniform, if that show that that f and x is uniformly convergent over the limit of integration, then you can interchange the limit and the integration operation. Okay. Later we will actually learn another way to justify interchange. That's called the dominated convergence theorem. In fact, for that one, you don't need to check for uniform convergence. Okay. In fact, for that one, you just need to show that your f and x is bounded by some function of x that does not depend on n. Later we'll study that, right? So there's another way to justify the interchange. But at this moment, since we learn uniform convergence, we want to show that one application of uniform convergence is to justify the interchange. Okay. All right. Then we move on to problem 7. Problem 7, there are 3 questions, right? Maybe let's try 1.
Yeah, it's me. It's my question.
1 is,
I will have to share screen right now.
yeah, okay.
Can you see my screen?
Yes.
Okay, so basically what I have to do is I have to show limit when n approach infinity for this integral and evaluate it. So first I prove that the sequence function here is uniformly converge to 1 when n approach infinity. So what I do is that I use the definition, the sequence function minus 1 is less than epsilon. Then as we know that because this integral is only we have to integrate from -1 to 1. So I set the condition as x is less than 1 and larger than -1. So it would imply that x squared is actually less than 1. So I will go to write this here, and I will prove that this inequality holds when we choose n is larger than 1 over ln epsilon plus 1. Theorem 3.6.1, we can know that the left-hand side here is actually can be written as the thing at the right-hand side here. So we can get integral as 2.
Yes, yes. Okay. All right, okay. I think it's clear. Yeah, thank you, Juan. So, yeah, well, if you wanted something more graphical, so you could have done the following, but it's okay, that was correct anyway. So this one, you know that this is an even function, right? Because if you change your x to negative, it still is the same as your x, right? In fact, you graph this, right? It will look like this. If you graph it, it will just increase like this, and this part is a reflection. Okay? So for n equals to 1, so this will be, so this line will be E1. Okay? So this will be 1. Okay? And so on and so forth. So in fact, this is actually equal to 0, 1. So you can put a limit here. Sorry, multiply by 2 times, yeah, because that is basically since it's symmetric, so you just do one piece. Okay, so you can do something, just simplify the problem like this, right? Then you basically want to show that this is uniformly convergent over 0, 1, right? Instead of showing uniform convergence over -1 to 1, it's okay to just argue that it's uniformly convergent over 0, 1. And of course, the argument that's given was sufficient. Okay, uniformly convergent to 1, so it's bounded by E of 1. And then you proceed to bound it with this, right? And this is always so this one you can remove the epsilon because this guy here is always at least equal to 1, right? So this difference is always positive. So you can rearrange and get the result that one showed, right? If you like the so visually that will be basically just something like this. So this is your 0, 1. That will be your E of x squared. So when you have n equals to 1, right? When your n is equal to 2, there will be e x squared over 2. That will be slightly less, like this. And you can start increasing your n, it will just go like this, right? Until in the limit, it should flatten out to the line of 1 here, okay? So from here, it's very easy to see that it will be uniformly convergent, because if you set arbitrary cutoff epsilon here, right, from your 1, you'll find that definitely like after there will be, okay, so all these are within, right? So this will start to escape. But as you kind of like move along, right, because they kind of like they flatten, you see. You set an arbitrary epsilon, right? For some n, it will start to go, surely it will start to go below that epsilon, right? Okay, so then you know that there is some threshold n such that after you have gone through that threshold, the tail sequence, right, they cannot escape from 1 with more than epsilon, right? So that of course you still have to argue formally using this, but if you first sketch a graphical way to represent this, then it gives you a lot of confidence that you are on the right track. Okay. Okay. So then after that, after you show this, you can interchange. Right. Okay. So let's move on to the next one. We have Farah. Is Farah here?
Yes, sir.
Yeah. Do you want to share your screen?
Can you see my screen now?
Okay, we can see it.
Okay.
Mm.
So for problem 7, number 2, so the first step is we need to find the pointwise limit. And for the pointwise limit, we treat the variable x as a constant. So after evaluating it, we have the pointwise limit of the sequence on 1, 2, 3 is the function f defined by fx equals to x. And then the second step is checking for uniform convergence. So here we have that the 3 to the power of 4 minus 3 over n is greater than the 3 minus x to the power of 4 over x to the power of 3 plus nx for x in the in 1, 2, 3. Thus, given that the epsilon greater than 0, taking n such that 3 to the power of 4 minus 3 over n less than epsilon, we will get a uniform convergence Fn approaching f on 1, 2, 3. So the third step is evaluating the limit and integral. So this one is following theorem 3.6.1. Since Fn is integrable on 1, 2, 3, so is the uniform limit f. Therefore, we will get the answer as 4.
Okay, Farah, can you move further up? When you show the pointwise limit, so it's equal to x. Okay, but your x, you treat your x as a constant, right?
Yeah.
Actually, wouldn't that, in the limit where n is very large, wouldn't that be equal to Right, okay, so you have this. Okay, then your second step, you have that. So let me just have a look. So you X. Okay. So you simplify that, yeah?
Yep.
Bounded by 3 power of 4 minus 3. Okay. Because the largest one that is possible is 3 power of 4, right?
Yes.
Okay. Then you pick n such that. Okay, so 3 power of 4 is what? 81, right?
Yeah.
81, yeah, so you basically, it's just 81 minus 3, that's 78. Yeah, okay, so you can find your n as 78. N has to be larger than 78 over epsilon, okay? So then uniform convergence, yes, you have that. So, okay, and then some more. Okay, goes to 4, all right? Okay, thank you, Farah.
All right, thank you, Lebesgue.
If you want to verify this using, you can verify this using if this still feels mysterious to you, maybe you want something more like concrete, you can verify it using Wolfram alpha. Okay, I'm just going to share this screen with you. Wolfram alpha. Share screen. Okay, do you see Wolfram alpha? Have you heard of Wolfram alpha before? So it's a very useful tool, at least for the things that you want to, like sometimes you do some integrals, you want to check whether it's correct or not. So you can actually use it for checking. Sometimes you're lazy to, you more or less kind of like know how to do it, but you're just lazy to do it and you want to check the result, like what I'm doing now. So I basically just showing you how to do the integral for, just ask, you can double check your work like this, right? So, okay, so I can ask it to do the integral for for that particular integral, right? In 2. Now, what does it say? All right, it says standard computation time exceeded, which is basically telling you that that integral is actually, if you try to do that integral, is actually going to be rather complicated, right? So why don't we ask it like, okay, let's take the limit of n. Actually, the commands that I put here, right, they are actually quite intuitive. Sometimes you make some small mistake, it doesn't matter. Wolfram is smart enough to understand it. So let's try to see what it says. Oops, it says nothing. All right, says computation time exceeded. So you know that this is not going to work if you, well, if you buy the full copy, it will give you. This is the free copy. So if something that exceeds the computation time by a certain amount, they just tell you that and ask you, well, do you want to consider buying this copy, right? So doesn't matter. We'll try something like this. So we try something like, let's make my n like quite large. Let's say I make it to be 100, and we see what happens, right? Let's try. Yeah, you see, you put 100, you get something like 3.84 because then instead of giving a general solution, Wolfram is basically using numerical integration. So it's very fast, right? So you can use this way to check. So let's try 1000. So you see, it gets closer to 4, right? Now it's 3.98. Well, let's add one more zeros. Yeah, 3.98, right? So I'm sure by this point you are pretty much convinced that it's going to tend to 4, right? Therefore, if Farah, you had used this tool to check, you would feel very confident about your results. Okay. All right. So this one, I'm introducing you a tool for you to check your work. In case you find that, okay, yeah, seems like the analytical steps seems correct, and you want to just verify it computationally for that added level of confidence. Okay. All right. Okay. So we just have one more question, so we quickly finish it. Although we are a bit over time. So last question, Nuru, Izati.
Hey, doctor.
Okay.
I will share my screen. Now, can you see my screen? Hello.
Okay, we can.
Hello.
Yeah.
Okay, so the question is to prove for limit n approach infinity, integral 0 to pi over 2, square root sine x over n plus cos x over n dx. So I let f and x equals to square root sine x over n plus cos x over n, which is x greater than 0, be a sequence function. We claim that f and converge uniformly to 0. To prove this, I showed that for all epsilon greater than 0, there is some n such that small n greater than n equal to n, then minus 0 less than epsilon. Then we need to recall that sine and cos function are bounded, since x and sine and cos take values from between -1 and 1. So the value of f and x will be between -1 and 1. So -1 and 1 is bounded for sine x over n, which is same with cos x over n. So -1 until 2, we bounded this function sine x over n plus cos x over n square root when n greater than capital N, since this function is bounded by 2. So we have sine x over n plus cos x over n square root less than equals to 2 over n, less than equals to 2 over capital N, less than epsilon. So we take n greater than 2 over epsilon, complete the proof. So by theorem 3.6.1, the limit of integral 0 to pi over 2 with the function. So integrate the limit, which is 0. So the limit is 0.
Okay. You left out the dx for the second last step. Yeah, the integral of 0 to pi over 2 of 0 dx. You left out dx.
Yeah.
The second
This
row. Yeah, this one. There should be a dx.
Okay.
Yeah.
Okay.
Yeah. Okay.
Okay.
Just move a bit further up. A bit further up. Okay, yeah, a bit down. Okay, I just want to check few steps. Move a bit down. You do the bound, right? So okay, but how come? Okay, it's okay to get these two bounds, but how does that give you the bound in the next step? Because if you, because if you add sine x plus cos, sorry, if you add the inequality on the left with the inequality on the right, you will get that sine x over n plus cos x over n is bounded by -2 and 2. Bounded between -2 and 2.
Yeah.
So how would that actually, how would that be? I'm just curious, how would those two statements there give you the next statement? It's a bit unclear.
I just plus this sine and cos.
Yeah, because if you plus them, right, they are just bounded between -2 and 2. So when you take square root, yeah, so what if you take square root, then something weird might be going on, because if that sum is a negative value, then when you take square root, it becomes a complex number. So I think we need to work out a bit more carefully on these steps, although there are some ideas, all right?
Yeah.
Okay, never mind. Thank you, Nuru.
Thank you.
So mainly you have to, okay, so you want to show that so this one is going to 0, right? Take limit. So we want to show that this one is bounded for this for all this if there is some n such that n implies that inequality. Okay. So yeah, so then we have to play with this inequality here. Now, I think first thing is that we need to know that this thing is definitely bounded by this thing. Okay. In fact, this will be further bounded by the following. Right, because this one, it can be positive or negative. So this part here, you have to bound it from above with this, and then you bound it further with this, and then therefore you can, okay. So what would happen here? So it has to involve some kind of here it has to involve some kind of a bound that involves some function of n. Okay. What might that be? So if you just directly bound it with 1, right? This is bounded by 1, then so this whole thing is just bounded by some constant, right? It does not involve your small n, and therefore you cannot manipulate to the form where this is some function of n, and where this is monotone, and then like this. You can't reach this step and show that, right? Okay, now since we are a bit out of time, so I will separately put this in the solution, and you can read it from there. Okay, so I'll show it from there. All right, so how to argue this part? So this part you have to play with the inequality a little bit more carefully. Okay, but otherwise the result is correct. Right, you just interchange the limit into the integral, and you can calculate the integral. Okay. So now, just quickly, I will go to the tutorial 3. Tutorial 3. So just to assign the questions, yeah. Screen sharing. Can you see tutorial 3?
No, doctor.
Okay. Can you see now?
Yes.
Okay. So there are 1, 2, 3, 4, 5 questions. Okay. So maybe we assign some students to do it. Who would like to try problem 1? Just show that those operations will lead to members in a sigma field. So this will test your understanding of what a sigma field is. Okay. 1A and B. Any volunteers? Any volunteers? Okay. Aishwarya will try question 3. One more, Hakima will try question 2. No, Amira wants to try question 5. And we are left with 4 and 1. Jaswani wants to try question 4. Okay. And question 1 just looks scary. It's actually quite easy. So any volunteers for question 1? No volunteers. If no volunteers, I'm going to assign. Okay. Who is Zishuang? Is Zishuang here? Is Zishuang here? Yes. Okay. Question 1 for you, yeah? Okay, just try it, all right? Okay, so sorry for taking up extra time. Okay, so that will be all for this week, and enjoy your holidays for next week. And in week 6, when we come back, I will give you an assignment, right? Continuous assessment, which I will give you 1 week to do, okay? So that will cover up to all the material in tutorial 3, all right? So next week, finish tutorial 3, and then we will have a continuous assessment covering the material up to tutorial 3, okay?
Okay.
Right.
Thank you very
Okay.
much, Doctor.
That's all for today. Okay, thank you, everyone.
Thank you, Doctor. Thank you, Doctor.